Hello and welcome back to the Geostatistics course for beginners with QGIS and R. This is the 5th lesson of this course, and today we are going to be talking about continuous random variables in the univariate analysis. I loaded already the Meuse Data Set, and today I would like to start talking a little bit about histograms. Then let's go to load the last one we created. It was the number 4, and I'm going to the layer is already loaded. The parameter is going to be sync. The number of bins is going to be 12. We talked about this information the other day, and now I'm going to add the labels. I added for the X is going to be the sync concentration in ppm. Then for Y is going to be the frequency. The title of the graph is going to be histogram, and the subtitle is going to be raw data. Then I'm going to run this one, and let's see. As you can see here, we have the frequency. It means, for example, how many samples we have in this range from here to here. In this case, we have almost 60. At the axis X, we have the sync concentration in ppm. In this case, we have a total of 12 bins, and what we can see here in this histogram is most of our samples are located at the beginning of the range. It is interesting to see that when we leave the software to decide what is going to be the weight of each bin, the software doesn't start at the beginning of the range. It started a little bit before and also a little bit after. And if we want to control that things in our histogram, we have to add a specific range in our histogram. And that is what we are going to do with the next script. We are going to add a specific range to be more accurate, and also we are going to add the number of samples in each bin to have a better visualization of our data. Then go to QGIS. I'm going to put this one here at the moment. Create new script. I'm going to paste the things I have already done. I'm going to make this one bigger, and all this section from here to here, you know already about all these things. And now I added to the interface these 3 new fields that is going to be relative with our range: the minimum value, the maximum value, and the interval, the range we want for each bin. Then if we see the interface, these 3 are the new sections that has to be filled. Then let's go to see more things related with this script. Also here I added this one to indicate that the y-axis is related with the count, the number of samples. Also for this section of the script, I added the breaks sequence that is going to be from X minimum to X maximum, that is our range, and also by the interval. That is the color for the lines and for the fill of the bin, the transparency. We know about all these 4 labels and themes, and also I added this new section of coding that is related with the information for the number of samples for each bin. Okay, now let's go to save this one. And I'm going to save this one as a number 6 is going to be count histogram count bins. Then save. Going to put this one like this, and let's go to fill all the information related with this script. Then number 6, execute, and the layer loads automatically because just there is one layer. Then it's going to be for the sync. This one is going to be the concentration of the sync. This one is going to be the frequency, histogram, and raw data. Now to add this information, we can check the attribute table to see what is going to be the range. Then let's go to the attribute table, And let's go to see what is the minimum value for thing. That is 113, and the maximum value for thing, it is 1839. Then let's go to add that information to the range. This one here, that one is going to be 113, and this one is 1839, but I'm going to add 0.01 to give the opportunity to the software to add the last value, okay? And the interval, we are going to make the difference between these two values, and let's go to decide how many bins we want, right? Calculator, then it's going to be 1839 less 113. And now if I want 12 bins, I have to divide this number by 12, okay? Divided by 12, I'm going to have how wide is going to be each bin. Then copy this one, and I'm going to paste over here. Oops. What happened here? I cannot copy. Okay, maybe like this. Copy and paste here. Okay, that's good. Then I can run, and let's see the graph. Hey, do you know the Geo RGB community has a Facebook page? I'm going to leave the link at the video description, then you can click and follow us in this page. I'm going to be posting some content here that you are not going to see on the video tutorials in YouTube. Also, remember, if you want to have access to the scripts that we are using at the course, go to the Geo RGB community website, go to courses, then click on this course, start the course, and then go to the lesson. For example, for lesson 4, click on the lesson, and here you are going to have the attachments related to the scripts that we was using in this lesson. Remember that I'm going to post the scripts exclusively at the Geo RGB website. Okay, let's go to continue. Now let's go to compare both histograms. In this one, the first bin has 65 samples. But in this one, the first bin has less than 60. And the problem is that here, the histogram started before of the smaller concentration that we have. In this case, the smaller one is 113 ppm, and maybe this bin started at 100. And we don't want that one. We want to have a data in the histogram that represents our range. And that's the best way to do that one. Also, there are some differences at the end of the histogram. As you can see here, we have 321, but here we have 311. There are some differences. In general, they are pretty similar, right? But if you see close, you can see the differences. And a histogram is a picture of the data set, right? How our data is distributed. And we want to have a picture that is inside of our range. And that's the reason because I show you how to do this kind of histogram, because it's more accurate. Also, with this histogram, we can decide how wide is going to be our bin, because we can add here the value that we think is the best to represent our data. And that's really important. Now, I am going to show you another script where we are going to make the interpretation of the histogram in a different way. Here, in the y-axis, what we have is the number of samples or the number of measurements that we have in each bin. But we can make the representation using the relative frequency. That is going to be how much represent each of these bins with respect of the total. Okay, let's go to do it. Then let's go here, QGIS. I'm going to move this one over here and this one over here, and I'm going to create a new one. Then I'm going to paste, and let's go to see how the script looks like. We know already about all these ones. That one is going to be the same as before, but what I added now, something new, is going to be this one. Okay, that's indicating that the count is divided by the sum of the count. Okay, with this sentence, what we are saying that is that we want the relative frequency. Okay, this one is the same as the other one, and you know about all these ones. Then I'm going to save this one as a histogram relative frequency. Going to be the number 7, and save. Let's go to close this one, and let's go to run the script. Is number 7, and the labels is going to be the same, but for the label at the y-axis, I'm going to put a relative frequency. The range and the interval for the bins are going to be the same. Then run. And let's see the graph. As you can see here, at the y-axis, the values change. If you compare with the other one, 60, but now here we have 0.4. Okay? And also one bin is disappear over here. And if we compare over here, then it means that we have to do a modification over here. Just add extra 3s. That's the problem. Then I'm going to run this one again. And let's see what happened now. Okay, now as you can see, we have the bin. Then I'm going to close this one. Now I'm going to show you in a spreadsheet how we have to interpret this information in this graph. Then I'm going to open Apache. Is this one, open Office, and I'm going to open an spreadsheet. Remember that if you want to download this software, there is a free software and also open source. You can go to the website, then go to resources over here, then go down, and you have to click over here, and you can download the software from the official page. Is this link over here. Then what I'm going to do here now, it's go to here to this one to see the number of samples for each bin. Then I'm going to add all these values over here, but I'm going to pass the video faster. Okay, now I have all the values, and I'm going to do the summation. Yes, that one is going to be equal to the summation. And I'm going to add all these values from here to here. I'm going to close this one. And the summation is 155. That's correct because that's the value that we have over here, right? If you check here from number 1 and the last one is 155. Okay, that's the total number of samples that we have. Then with this operation, we know that all this data is correct. Okay. Now what I want to know is how much it represents each bin with respect to the total. Then I'm going to do this relation. If 135 is the 100%, right? Then, for example, 65, that is this value, how much it represents is going to be x, okay? Because we don't know this value. Then that one is going to be equal to this one multiplied by 100, 65, 100 divided by 155. And then I'm going to get the percentage. It represents 41.9% of the total of the samples that we have. Then I'm going to copy this equation over here, copy, and I'm going to paste here, special paste, and it's going to be as a formula, okay? Then okay, and I'm going to do some modifications here because 65 is this value. And 155 is this value. To make this value constant, I'm going to add here the dollar symbol like this, and then I can copy and paste the formula for all these ones. And now the summation of all these ones has to be 100 because that's the total. Here we go. Now let's go to see on the other graph, this one that has the relative frequency, and I'm going to put this one next to the graph. And as you can see, for 65, that is the first bin, it represents almost 42%, right? Because it's 41.9, it's almost 42. And that's the information we can see here. That one is going to be the 40%, 30%, okay? And this value over here is going to be for 42%. Then the next one has 22 samples, as we saw on the other graph, okay? And the percentage, it represents the 14%, okay? That one is going to be 15 at the white line, but we have 14%, okay? The next one is 9%, okay? It's this one, and so on. Then this graph also is really good because just with one glance, we can see a lot of information. We can see that the first bin almost represents 50% of all our data set. And that's a lot, right? It's pretty significant, okay? Also, we can see that for the last bins, the representation it's very low. We don't have too much samples. We can see this information over here, right? With the number of samples. But here we can see that one in the relative way because we have the percentage. Now let's go to see another different way that we can make the interpretation of a histogram. That is going to be with the density frequency, and that histogram is going to help us to understand the probability density function that we are going to define later, okay? In this new case, what we are going to do is for each bin we are going to have the area, and the summation of all the areas for all the bins is going to be equal to 1. That's the density frequency. Then I go to QGIS, go here, going to move this one over here, create new script, and I'm going to paste over here. I am going to make this one bigger. And for all these ones, we know already how it works. It's going to be the same as before, but here in this case, what we are going to add is this one, that we are seeing the y-axis is going to be the density, and for the rest of the things is the same as before, okay? Then I'm going to save this one as the histogram density frequency, the number 8. Save, and now I'm going to close this one and I'm going to run that script. As I said, it's number 8, this one over here, and the labels, the information here is going to be the same as this one, but the only thing is going to change is the label for the y, that we are going to add a density frequency. Okay, I'm going to copy and paste the values. Now I'm going to run the script, and I'm going to open. Again, we are missing here one bin. Then I'm going to change this one over here. Then here, I'm going to add more decimals over here. And also what I saw here, I don't know what happened. When I copy and paste, now I have one number less. Here is 112 and here it was 113. Then I don't know why, but be careful and double check all the numbers. Extra decimals here. And let's go to run again. And now we have the bin. I have different tries, but I didn't record that ones, but you can see that tries over here. And the problem, as I said, it was when I copy and paste, it changed one point over here. I don't know why, okay? And I was getting crazy because I don't get the bin I needed, and I couldn't find what was the problem, right? It took me a bit, and that was the problem. Now I can remove this one, even if you can see the histogram is different. This one is different. the beans change over here and also over here. That's a wrong one, but this one is the same as the other ones. Okay, and now here we have the density frequency. It means that the area of all the beans, if we plus all the areas, we are going to have 1. Okay, and that's important to make the definition of the probability density function that we are going to do now. At the previous lesson, we was doing the definition of a random variable, and we saw this definition. Random variable in statistics is a function that can take on either a finite number of values, each with an associated probability, or an infinite number of values, whose probabilities are summarized by a density function. Okay, that's the function that we are going to see now, but also here is summarized by the cumulative distribution function, because it gives us the probability also. As we saw the other day, the cumulative distribution function can give us also the probability, right? It's the accumulation of the beans, and with that accumulation we can create a graph, and from that graph we can extract the probabilities at the y-axis from any value in our range. Okay, but now what we are going to see is the probability density function. And the probability density function, known as a PDF of a continuous distribution, is defined as the derivative of the cumulative distribution function. Okay, we are going to say that the probability density function is defined with f as a lowercase. Okay, and what interesting thing is that the integration of the probability density function is the cumulative distribution function. Okay, if we take the cumulative distribution function, that is this one, that is defined as a capital letter, and then we make the integration of the probability density function, we are going to get the cumulative distribution function. And also one important thing is that all the area under the curve for all the range is going to be equal to 1. Okay, and it is defined with this equation over here, right? The probability density function, if we make the integration from minus infinite to infinite, the result has to be equal to 1. Also, for this function, we can calculate the probability associated with a specific range of our data. Okay, if we calculate the integration, for example, from here to here, and then we get all this area, that is going to be the probability of getting a sample in this range. Also, with this function, we are covering the fundamental assumptions related with the probability. Our probability is going to be equal or bigger than 0 in all the range, and also the summation of all the probability is going to be equal to 1. Then that is what happened here. All this area, let me change the color. All this area under the curve is going to be equal to 1, and that's the total probability. And also what we are not going to have, it's a curve that is doing something like that, then goes like that, and go like that and like that, because here, as you can see in this area, we are going to have a negative probability, and that one cannot be possible. Okay, then the curve always has to be above of the x-axis. This probability density function, it's I'm going to say a sophisticated way of doing the histogram, because just with one curve you can see the distribution of your data. But from my point of view, in terms of calculating the probability, the other curve, this one, the cumulative distribution function, is more intuitive than the other one, but that one is more popular. Now let's go to see how we can make a script to make the interpretation of this curve. First, we are going to create a script where we are going to add the histogram and also on the top the probability density function. Then new script, I'm going to paste over here. I'm going to make this one bigger. All these ones are the same as before, but what I'm adding now is this information. This is related with the curve of the probability density function. That's the only new thing we are adding here. Be aware that we are working now with density for the y value. Then I'm going to save this script as number 9, and it's going to be probability density function and histogram. Then I'm going to save. I'm going to close this one, and I'm going to run the script. It's number 9 over here. And for the labels, it's going to be the same as this one, density frequency for y, but for the title, I'm going to add probability density function plus histogram. Then I'm going to copy and paste all these values, but I'm going to pass the video faster. Then I'm going to run. And I'm going to see the graph. What we can see in this graph is the histogram and also the probability density function, and both are in the density frequency. Okay, and as we saw, the curve tried to adapt to the shape of the histogram, but the result is not really good. Also, in this curve, if you make the integration from 113 to 1839, the area that you are going to get from the curve is going to be equal to 1. Also, if you are making the summation of all the areas with all these bins, the summation is going to be equal to 1. But what happened for the probability density function is, if you want to have a really good adaptation of the curve to the histogram, you need the bars to be very, very, very short. It means that in a very small range of a very small area of your range, you need to have a lot of data of information. Then my recommendation is, if you don't have a lot of data, if your data set is not really, really, really big, don't use the probability density function to show the distribution of your data, because as you can see, it is not bad, but it's not the best, right? Because there are a lot of gaps of information. Even if we try to have a better adaptation of this curve to the histogram, maybe you are thinking that we can add more bars, right, to the histogram to see if the curve improve, right, the adaptation. But you are going to see now, because I'm going to show you that if we add more bins, even we are going to have more lags of data, because the distribution of our bars are not going to be continuous. And that's also a different kind of problem, because we want the data to be continuous. Okay, I'm going to show you now the new histogram with more bars. Then I am going to use the same script that is going to be this one, but the only thing we have to change is this one, the interval. Then here we put 12. Then I'm going to add, for example, 50 to see what happened. Then I'm going to make the difference here of 1839. That's the highest value, less 113, that's the minimum value, equal, and divided by 50. That is going to be the number of bars. That one is 3452. Then that one is going to be 3452. Then I'm going to run this one to see what happened. And that's what I said previously, right? As you can see now, we have lags of data, and our data it's not presented in a continuous way. Also, the data has been more spread. As you can see over here, the curve gets more soft, and also that is not good, right? Because as we have 155 samples, we cannot make a histogram with 50 bins because that's too much. We spread the data too much, and also we have that lack of information that it's really bad. And my recommendation is no use this amount of bars just to trying to adapt the probability density function. Then you can use that probability density function, the interpretation of the graph, when you have a lot of data, and then you can make your bins very short to try to adapt the curve the best way. Now I'm going to show you a script where we are going to plot just the probability density function without the bars at the back. Also, I use different colors. In this website, you have a lot of colors that you can use with ggplot2, and you have here the names, and that's what I was using to create these colors for these graphs. I'm going to leave the link of this website at the file in the website, with also the scripts I'm using for this lesson. Then go here, let's go to create a new script, new one, going to paste here, and that one doesn't have nothing special, everything is the same as before, ggplot, and the only thing is that we remove the geom histogram and we leave this one, and that's the way we are going to create the algorithm to make the representation of the probability density function. Then I'm going to save this one, that one is going to be number 10, and I'm going to save just as a 10 as a probability density function. Save. I'm going to close this one, and I'm going to run the script. Oh, it's over here after 1, number 10. Okay, I'm going to add here the same parameters as I added over here. Okay, I'm going to copy and paste and pass the video faster. Then I'm going to press run. Okay, put the bins for this one, just with 12 bins. Okay, run. And let's see the graph is this one. This is the end of the video, but first I would like to do a summarize about the probability density function. As we said previously, the function has to be always positive, equal to 0 or bigger. We cannot have a negative probability. Also, the integration between minus infinite and infinite is going to be equal to 1. That is the total probability under the curve. And for any interval that we are doing the integration, for example, from A to B, as you can see here, we can get the probability of getting a sample in this range of under the curve. Okay, the area is going to be the probability, and that's the definition. Okay, thank you very much for watching this video, and see you on the next one.